So, very good evening to everyone. So a very good evening to everyone. So I am Rohit Gehlot and I will be taking this tutorial of Principle of Casting Technology for the week 2. So am I audible? Can anyone confirm it?
Yes, sir, you are audible.
Okay, thank you. So today the major focus will be on the some solving some numericals, and I will also be solving with you and to amplify some concepts which were not like covered in the classes, the recordings. So firstly, if we talk about the shrinkages, like what are in the theory also, like some of it has been covered, but as the numerical portion was missing, so I thought to again uh, like uh, again teach some like concepts of basics. Then it will be shortly I will be teaching this concept, and then we will move to the numerical problems. So firstly, if we like talk about the pattern allowance, so what is it like? So a pattern allowance, these play an important role in obtaining adequate patterns. So so whenever we are making a pattern or something, so basically it is a replica of a device which is produced by the casting process. So when molding in the sand, this forms a mold. When molten casting is formed after the molten metal is poured into the mold, and they play a very important role, because the final casting's quality is dependent on it. And in the next weeks or the further weeks, you will be reading about gates and runners and the design, and we will be solving about the numericals also. So as you can see, like in this curve, there are three temperatures mentioned: TP, TF, and TA. And so whenever we are pouring our molten melt into something cavity, this TP is basically the pouring temperature, which is always higher than your melting point of the particular material. And after that, when we pour, then it is in completely liquidous state. So after that, there will be some sensible heat loss if it needs to be converted into if it needs to come to the ambient temperature. Then after that, after losing some sensible heat, there will be some latent heat loss. This will be during the phase change, and after this phase change, or we can say like the latent heat loss, then there will again will be some sensible heat loss to come to the ambient temperature. And in the theory, it was defined that there are three types of shrinkages. One is the liquid shrinkage, another is the solidifying shrinkage, and the third one is the solid shrinkage. So if we talk about the liquid shrinkage, uh, so it is the contraction that occurs when liquid metal or alloy temperature falls from the pouring temperature to the liquidus temperature. This is in this region. After that, the second one is the solidification shrinkage, which is the contraction result of the cooling from the liquid to the solidus temperature. This will be due to the latent heat loss, and this will occur in this region. And then third one is the solid shrinkage. This will happen in this. And this liquid and the solidification shrinkage are like compensated in by the riser, and the solid shrinkage is compensated in by the pattern. And for any pattern for any pattern, the total shrinkage is given by the summation of these three shrinkages, which is the liquid shrinkage, solidifying shrinkage, and the solid shrinkage. Now there are, in theory, it was covered like there are various types of shrinkages. So in short, if we say one was the draft allowance, another was the shrinkage allowance, and then there was some distortion allowances, machining allowances. There are like different types of allowances. So firstly, if we talk about the draft allowances, it is generally provided to uh, it is given as a clearance basically. Uh, it is provided in taper form. And it is provided by the pattern maker on all vertical surfaces. I think someone admitted. Let me. Okay. So we were at the different types of allowances. So if we talk about the draft allowances, as I covered, so it helps for the all vertical surfaces to in the removal process when after the cooling down of our melt, it helps them to remove without tearing away the sides of the sand mold and without excessive wrapping by the molder. And then after that, if we talk about the shrinkage allowance, as we covered, there are three types of shrinkages. Two types are covered by the riser, and while we need to compensate for the third one, which is compensated by our pattern making in our pattern making step. So which we give. So all mostly all cast metals shrink or contract volumetrically on cooling. And then after that, if we talk about the finish allowances or wrapping allowances, finish allowance is basically the machining allowances. After making the mold, the surface is not generally very smooth. It is very rough and it needs some finishing. For all the casting processes, the surface is not smooth. There are like uh, advanced casting processes available, whose surfaces are very smooth, but still generally these are adopted. These costly processes are adopted for very high-tech applications, but for in general purpose castings, we need to machine over a final product, and therefore some allowances are needed. And then we talk about the wrapping allowance. So before the withdrawal from the sand mold, the pattern is wrapped all around the vertical faces to enlarge the mold cavity slightly. So and it is the negative allowance. Okay, and it is generally applied only to those diamonds that are parallel to the parting plane. Okay, then so I think it is time to move for one short numerical. So and then the question is firstly let me. So the question is a grey cast iron block of size 100 mm by 50 mm by 10 mm with a central spherical cavity of diameter 4 mm are sand casted. The shrinkage allowance for the pattern is 3%. The ratio of the volume of the pattern to the volume of the casting is very like, uh, like we can say it will clear your basics. So firstly there is oh, sorry. So firstly we can say there is a grey cast iron block. This is 100 mm. This is 50 mm. And then there is 10 mm with a central spherical cavity of dia. There is some cavity which has 4 mm diameter. Then there is some shrinkage allowance for pattern is 3%. So anyone who would like to try this problem and give the like what will be the ratio. After that, I will be solving it for you. There are like three very good questions. Like and after these, after the first two questions are for the basics, and then the third question is very good. Like this will after if you can like if you will be able to solve the third question like majorly the you can solve any type of problem in the in the pattern and allowances. So I would request all of you to please try this. So today like there are only two people who joined like so Vishal and Sanjay. So are you trying this problem Vishal and Sanjay? Are you here? Okay then so like I will be solving this problem like to tell you like how we can proceed with this. So as it is given like the shrinkage allowance is like 3%. So like the shrinkage allowance will be like given on each side like 100 mm, 50 mm, and 10 mm. While on the diameter part, we need to I will like show you like how do you so if you write so your length will be needs to be increased by this factor, and similarly the width also needs to be increased by the same factor like as the as it is not said like for all the three sides the shrinkages are different. The same for your length, width, and your height. So like this will be your final sides after the increment of your like after taking care of the shrinkages. And then if you talk about your central one, so firstly the volume of the pattern, firstly the volume of the casting. If we say, can anyone tell me like what will be the volume of the casting? You can try, like it is not a tough problem. Like if you will try, like if it will be a discussion, like healthy discussion, then you learn more. That's why I'm saying. Sanjay, you wanna try this? Okay, then so the volume of the casting will be, as it is cuboid, so the volume will be like LBH simply. The volume of the casting will be like 100 multiplying by 50 multiplying by 10. However we need to subtract the central spherical cavity, and whose volume will be like 4 by 3 pi r cube. So this will be the volume of the casting. Now if we talk about the volume of the pattern, we simply need to like consider all these three sides with their respective shrinkage factors. So finally 100 will be like taken as 100 multiplying by 1.03. Here width will be taken as again 50 multiplying by 1.03, and then comes your height, which will also taken as 10 multiplying by 1.03.
Hello.
Yeah, hello.
Yeah, Rohit. I am trying this problem. I told you many times, but I think there was a problem with my microphone.
Okay, okay, okay.
So,
So,
so actually, I have a doubt. How have you taken this? Is it 1.1.03 into 100 and 50 into 1.03 and 1.03 into 10, right?
yeah, right, right. It is 10. So like
So
basic. Yeah, yeah. Please go
yeah,
ahead, please.
how is it 1.03 in all of length, width, and height? Is it not supposed to be 3% of length and 3% of width and 3% of height, which means 3% of 50 and 3% of 10 as per the shrinkage?
Okay. So basically, it is given like uh, the shrinkage allowance for the pattern is 3%. Okay, right.
Yes.
So yeah, yeah, you're right, right. So I thought I didn't. I did a mistake. You are right, completely right. So we need to like do it like 3% for so like 100 3 we need to take 3% of 100, then 50, then 10. But generally like you understand the what is the procedure we need to follow, right? And again like if we like talk about the central cavity, so again like we need to like subtract 4 by 3 pi, then r will also be like taken 1 point so like if you say like the shrinkage, actually here in this problem the shrinkage allowance for the pattern is like 3%, right? So whatever you do, like I am also doing the same thing, like so if we say if you see like the sink if it is an increase, any side is increased by 3%, so it will be like if it previously if it was 100, then it will become like 103, right? And then if again it is divided by like 100, then it will be 1.03. So each side will be increased by 1.03 itself, right? If you do like it the conventional way, like 50, like if you increase like 50 mm, suppose if you say like you increase width by 3%, like 50 into 3 by 100, then you will have to add it to 50 mm, right? So you will write it as 50 plus 50 in multiplying by 3 by 100, right? So, and if you take 50 common, then it comes like 50 in bracket 1 plus 3 by 100. And again, if you take the LCM, it will be 103 by 100 itself. So it is the same thing which I am doing, and you are right. But you will again have to add it to the original side. There, then only it will be like taken as the totality increment in the totality, right? So am I clear, Suraj?
Yes, yes.
Okay, thank you. Yeah, Sanjay. Sorry, I took your name. So now if you see the volume of the pattern, so it will be like 4 by 3 pi, then factor will be increased by 1.03 for its radius side. So these are the like two volumes. Now if you calculate them and then divide them, then you will get the ratio of the volume of the pattern to the volume of the cast. Can you like please solve this and like tell me what is the answer you are getting? So
Rohit, I did not understand the volume of the pattern here. Like, on what basis you have written this formula? Could you please explain?
okay, so if you firstly consider read the question again firstly it is written that there is a gray cast iron blocks, like so you imagine a cuboid in your like mind which has like 100 by 50 by 10 mm sides for its length, breadth and height, right? And then imagine like it is like at central it has like hollow cavity which is a spherical cavity basically, okay? And with a diameter of 4 mm. So you imagine this is like a diagram for like another question, but you imagine like there is a cavity in the center which is like 4 mm dia, okay? So are you like able to imagine now?
Yes, I am able to imagine the cube, whatever you said, but volume of the pattern, we have
Okay,
written it 100 into 1.03 into 50 times 1.03 into 10 times 1.03 minus 4 by
yeah.
3 by r cube. So
So you
why?
want, yeah. So firstly like you understood how the volume of the casting was taken, minus 4 by 3 pi r cube. You got it.
I understood it in the first formula, that is volume of casting. That is,
Okay,
but in the second formula, why should we subtract when it is
yeah.
one?
So this is the catch here. Generally firstly we need to like subtract it definitely. Then the reason is it is a, and because it is a hollow casting, right? Okay. So if it is a hollow casting, then obviously for calculating total volume we need to subtract the spherical one, right? And then if you say about the uh, like in 11th or 12th class we used to do like calculation for there is a rectangular like farmhouse or something, and then we need to fence it like outside with some of the uh, fences and all. Then what we used to do, like used to like calculate the total volume, then we used to subtract the central or like outer periphery, right? This is the same thing here. You have a block of this particular dimensions and the central spherical cavity which is a hollow one. Oh, so and then what happened? We gave the shrinkage of 3%. Like okay, so because what happens in the spherical cavity, like it is not the same with the other dimension. If it is a spherical cavity, you need to other parts you need to increment it, but while the spherical part you need to decrease it, because if you will because when you put your pattern or like something, these hollow part will behave differently, like, so than the other things. Because if you try to imagine you have a hollow cavity, and then after like solidification, how it will behave, you see, other part, okay, it will be increment, but this part you need to give it like a smaller smaller one. So it's majorly on the imagination power. Like if you like we'll proceed with the problem 2 and the problem third, it will be clear more. Okay, so we will go step by step. Firstly, you see like what is happening here. This is a basic general question. After that, when you will be going till question number 3, it will be completely clear to you. Okay.
Okay.
Okay. So whenever we need to design a bore or like hole, its shrinkage is always negative. So we need to reduce this dimension for getting the proper dimension for the hollow spherical cavity or for a bore. While for the other parts, it is the other one, other thing. So should we move to the another problem, or we still need some more time to have it?
Yeah, you can proceed with the next problem.
Okay. So if you will solve this, the ratio will be coming around like 1.08 something something. So by approximating, it will come around 1.09. So this is the second question. It is also a simpler one. So we need to design a pattern for casting which is having a dimensions of length 200 mm, width 100 mm, and height 80 mm. It has a central circular hole with having 80 mm diameter. Same as before. The casting is made from the steel. So in this summarizes for different materials what is the for 1 meter how much increment in its length will be happening. Like for cast iron, then it is negative. Like for cast iron, it is 10 mm per meter. For brass it is 16, for aluminum it is 15, and for steel it is 20, while for lead it is 24. So we need to design a pattern for steel. Okay, so we'll try to solve it, then we see how it is done. You basically you then need to calculate length, width, and height for a steel pattern whose shrinkage is given. Previously it was given in percentage form. Now it is given per meter how much increment or decrement will have. Just remember, for the central uh, spherical central circular hole, the allowance will be negative, while for the other it will be positive allowance. It will be additive, while for this the negative allowance, while for the circular cavity it will be negative one. So try to give me tell what will be the length, width, height, and the diameter of the pattern. And given that it is a steel. So anyone got the answer for this, or can you tell like what are the procedure they are following? This is a simpler one than the previous question. So what you can do for steel, like it is given for 1000 mm it is 20 mm, right? So you can calculate it in percentage, like the increment it will be having. So and then you can calculate that factor and then multiply it again in the for length, width, and height the casting is made for steel. So we need to consider for like 20 mm for 1000 mm. While for another also like it is given for your reference, like just to see how different materials behave. What are
So why it is 1,000?
like it is given that these are the standard one, like after the experimentation, and then the and it is 1000 because it is given like 20 mm per meter, right? Like for 1 meter length of the steel cast or ingot, you will have like 20 mm. Your pattern need to be like it will have like 20 mm shrinkage, right? So that's bigger you need to make your pattern to compensate that shrinkage. Else you will be having lesser length, width, and height and dias pattern, which you of lesser dia or like of your casting, which you don't want, right? So that's why these are the standard ones. Like for particular material, generally it is same like for cast iron, it is in the range of 10 mm per meter. Like for 1 meter,
So for
yeah,
steel, it is 20 mm per meter, which is 20 by 1,000. That is, you will get it to zero point 0.2, which you multiply by 100. That is 2% of
yeah,
shrinkage.
yeah, right. Now you got the 2%. So then again you will need to do the same thing for the length, width, and height. What we did for the previously, right? Like 1.02 factor, or like the conventional process, like you were saying, we can do it like 200 plus 200 multiplying by 0.02. Like that's how you will get the length, width, and height. So the length will be 200 plus 200 multiplying by 0.02. The catch is just to like tell like how different materials behave. It is like this one. This question is for like the steel one. So we need to like see we need to focus on each point. Like some people may miss this steel and then they get confused in numerical the it is not given this and that, but we need to like focus while solving the numerical on each point and on each line similar. So by calculating the length we will get like around 204 mm, and then the width will be you will be getting by 100 102 mm, and then the height you will be getting is then if you talk about the diameter, as I told it will be like negative one here. So it will be 18 into
So any reason why it should be negative for the pattern? Like,
Yeah, like we firstly you try to imagine it in your mind, like the how the hollow thing will behave, right? So after like everything will like length will be increasing and all, but the how the hollow part will be behaving, you try to first imagine, like we will like hold it for like 4 to 5 1 or 2 minutes, you try to imagine, then again we will come to like question number 3, then after that it might strike in like it is like completely on imagination, like how it is like happening, why it is happening. That's why I deliberately put this question here, because these 3 questions are like similar, like but the third one is a major one, like third question if you are able to thorough it, like but these questions like which are not covered in the like in your class examples, but these may come in your like further exams and all, to like you just focus and try to imagine it, okay, like what will be happening in a circular hole, why it is negative.
so you mean to say when the molten metal is poured in the pattern, that is the center circular hole,
Yeah,
where, when compared to others, like the sides, when the rectangular sides, when we pour the metal to that kind of a mold, so they try to shrink, but
yeah,
this hole will try to expand. That's what you're
yeah,
trying to tell. That is why
yeah,
we are taking it as negative.
yeah, that is yeah, that is what I'm saying. But if you will see any video on YouTube, like there are a lot of videos now available, like in which they are pouring, and then after, and then if you will see those, and then if you will try to imagine again, maybe it like strikes, because the circular hole, central hole behaves differently, and also there is like a thing like parallel or perpendicular to the parting line, like how it behaves and all. So generally and also it depends on location to location. The casting process is it seems very easy, but it is like a lot of calculation and and engineering, like how and what amount of material should be poured, how each component will behave, and like how it is very. So is it a little bit clear to you, like, or are you able to like imagine it?
Yes, now it's clear. I understood.
Okay. So any other people who has any doubt in this, like, or is anyone on the same page, like are they able to like solve this? So should we move to the third question, like, is it okay?
Yes, please.
Okay, okay,
Please
okay,
move to the third
okay,
question.
okay,
Complete as it was fast as possible.
okay. So this is like the third question, like determine the dimension of the pattern for casting shown in the figure. Okay. So here the shrinkage allowance is 20 mm per meter. Then the machining allowance on all the surface and the bore, which is diameter, is 1 mm and 0.75, and 1 degree draft allowance for external and internal dimension. Okay, so what you need to do, like, firstly you will do it for the shrinkage allowance, right? Then you will do for it for the 1 mm and 0.75. This is the taper thing, like the top side it is like 1 mm, while at the bottom side is 0.75, and then finally the machining allowance is given as 1 degree. So firstly the shrinkage allowance we are doing, we have already solved 2 problems. So shrinkage allowance can be done easily for like each side. I think I put the dimension. So I think this I have the answers for the 200 mm side, 100, 150, and 60 mm side. Okay, we need to solve this. Yeah. So for the shrinkage allowance, we can directly do like what we were doing previously. So directly we can add like length will be like 200 plus 200 multiplying by 0.02. Similarly length, width and height. So and then after add, and for the diameter one, central one, it will be considered as a negative, like 60 minus 60 multiplying by 0.02. Then that's how we will be getting the solution for the shrinkage allowance, right? And after shrinkage allowance we need to consider for the machining allowance. Okay, so machining allowance is generally like, as it will be given on both the sides, right? So it will be what you will be getting. After the shrinkage allowance you will add here in the machining allowance. Like suppose you got the answer for the side 200 as 200 plus 200 multiplying by 0.02, 204 you got after shrinkage allowance. And after machining allowance you need to add it like as it is added on, as it is given on both the sides, so you will add like 204 plus 1 plus 1. So that's how you will be getting. And similarly for the central core you need to subtract again two times. Okay, so then that's how you got the machining allowance. And then after that you need to like take care of the draft allowance. Okay, so on the top it is like so draft allowance is generally as it is given in degree, uh, like 1 degree draft allowance, right? So and 0.75 I think machining allowance and also okay. Yeah, so on machining allowance on all the surface and the central one is 1.1 mm and 0.75 and 1 degree are the draft allowances. 0.75 is for the top side and 1 degree is for the bottom one. So draft allowance you will be calculating by, if you see as it is a taper, so we need to give that some angle here. Then if you will be calculating in terms of tan theta for 0.75 and 1 degree. So and then you will be like getting the final figure, like what will be the length, width, height and diameter after considering all the three allowances. So try doing this, give it an attempt. Like please tell me, like after the shrinkage allowance these are the length, width, height and the dia, and after the machining allowance these are the length, width, height and dia, and after the considering the draft allowance these are the length, width, height and dia. So this is the question. So the first part is the very simple one, like if I do consider the shrinkage allowance, then here the length will be, I will write for one and then can proceed like for other. So the length will be 200 plus 200 multiplying by 0.02. It will come around like 204 mm. And then your width, we do same thing, then 100 plus 100 multiplying by this, then it will be coming around 102 mm. Then your height will be 150 plus 115, 153. Then your dia. So this will be previously a 60 mm diameter. Okay, so as it is negative, then it will be around 58.8. So these are the result after of each side after the shrinkage allowances. So so is everyone able to catch me till this point?
Yes, yes.
Okay. Now if you consider the machining allowances. So as it is like for each side as it is given on both the sides, so it will be added twice. And as it is given that the machining allowance is 1 mm for each side. So then the length will be, we need to take now the consideration of the shrinkage allowances after shrinkage allowance. So as it is 204, so we will add 1 mm plus 1 mm, and then your length will be like 206. Then your width will be like same 102 plus 1 plus 1 as it is given on both the sides.
So machining allowance, why it is considered only on two sides? When the cuboid has six faces, or uh, like how the calculation for the machining allowances is taken only on two
Yeah,
sides?
yeah. So if you see like, can you see my cursor moving?
Yes,
Uh,
yes, yes.
so if you see like this part, right? Okay,
Okay.
200 part, this one,
Yeah,
and then the top one. These two are the 200 mm, right?
yeah,
So you will machine these two things, right?
yeah.
After, so the machining allowance for each side is 1 mm. So this one is 1 mm, this one is 1 mm. So you add 2. Similarly for 150, these two sides.
Oh yeah, got it. Got your
Okay,
point. Okay,
okay,
I got it.
okay, okay. Then if you like consider about the height, then it will be like, you have 153 plus 2, 1 plus 1. So you will have 155. Now if you consider the dia part, okay, then it is a negative allowance, like as previously mentioned. So it will be like again 58.8.
So for the central hollow diameter, like all the allowances are to be considered negative.
Yeah, right, right.
Okay.
So it will be as it is 1, so we need to subtract it 2 times, right? So it will be then 56.8. So till now I think oh sorry. So I think till now everything is clear, like, because now like, so I will erase some part. So I'm making some. So so after like considering all these, my these two allowances, my length I have at present is like 206. This part is 206. My width part is 104. My height part is 155. And my dia part is 56.8 after. So is it clear till now? I hope it is.
Yes.
Okay. Now the now will move to the draft allowances part. Okay. So I think I should draw this. So what it is mean? What is it like? What it is meaning with the draft allowance? Firstly, like firstly, have you tried it by your own? Like how we can Are you able to imagine like how your cuboid cube will look after giving it as a draft allowance?
So draft allowance is nothing but a slight deviation which is given into the pattern, like towards the inner side of the pattern,
Okay.
which results in kind of a triangular,
Yeah.
a little tapered kind of a
Taperedness.
cube.
Right. Right.
Yes.
Yeah. So you're right. Like firstly, in our question, it is like given 0.75 and 1 degree. So it is like uh, for external part it is like 0.75, and for internal taperness is like 1 degree. Okay. So after like firstly like after you're like this is how your pattern will look after giving it to the taper allowance. Okay, this is just I am not making a good figure here, but just for your imagination. And then here it is the angle theta, this part. Okay, and then these sides 206, and then this and this. So try like what will be the dimensions? Try it once. Like
So actually, the theta is supposed to be on outside of the diagram, right?
these two things, right?
Yeah.
After so the machining allowance for each side is 1 mm. So this one is 1 mm, this one is 1 mm. So you add 2. Similarly for 150, these two sides.
Oh yeah, got it. Got your
Okay,
point.
okay,
Okay, I got it.
okay. Then if you like consider about the height, then it will be like you have 153 plus 2, 1 plus 1. So you will have 155. Now if you consider the dia part, okay, then it is a negative allowance, like as previously mentioned. So it will be like again 58.8.
So for the central hollow diameter, like all the allowances are to be considered negative.
Yeah, right, right.
Okay.
So it will be as it is 1, so we need to subtract it 2 times, right? So it will be then 56.8. So till now I think oh sorry. So I think till now everything is clear, like because now like so I will erase some part. So I'm making some. So so after like considering all my these two allowances, my length I have at present is like 206. This part is 206. My width part is 104. My height part is 155. And my dia part is 56.8 after. So is it clear till now? I hope it is.
Yes.
Okay. Now will move to the draft allowances part. Okay. So I think I should draw this. So what it is mean? What is it like? What it is meaning with the draft allowance? Firstly, firstly, have you tried it by your own? Like how we can you are you able to imagine like how your cuboid cube will look after giving it as a draft allowance?
So draft allowance is nothing but a slight deviation which is given into the pattern, like towards the inner side of the pattern,
Okay.
which results in kind of a triangular,
Yeah.
a little tapered kind of a
Taperness.
cube.
Right. Right.
Yes.
Yeah. So you're right. Like for firstly in our question it is like given 0.75 and 1 degree. So it is like uh, for external part it is like 0.75, and for internal taperness is like 1 degree. Okay. So after like firstly like after you're like this is how your pattern will look after giving it to the taper allowance. Okay, this is just I am not making a good figure here, but just for your imagination. and then here it is the angle theta, this part. Okay, and then these sides 206, and then this and this. So try like what will be the dimensions, try it once, like.
So actually, the theta is supposed to be on outside of the diagram, right? You like
Yeah, yeah, it is like it is given for both actually, for internal and external. Two theta is given na. So the
oh,
0.75 is, it is for the external tapers. So your your shape will be like something like shaky thing of shape.
okay, okay, okay.
Okay, and generally like horizontal things are not affected by this, right? Are you able to like imagine why horizontal parts
E-
will won't? Yeah.
yeah, yeah, yeah. Only
Okay.
vertical ones you're telling about.
Yeah, only vertical parts will be, yeah, will be affected by this steepness. So like, can you tell me like what will be happening to the external part, like 155 mm height?
So the height will be reduced by tan inverse of 0.75. Is it that or
Yeah. So firstly, the external part which is like 155 mm. So it will be like 155 into 10 of your angle is 0.75. This will be how your length will be increased. Okay, you need to increase it for the externally. Okay, so it will come around, if you calculate, it will come around 2.02, which can be approximated. We will taking it as an approximate 2 mm only. So if you take now, if you like consider the draft allowance, so this is for the outer side, and then if you consider it for the inner side, it will be like 155 into 10, 1 degree, and it will be coming around 2.7. Okay, and then similarly for the diameter part, again you need to like subtract it, like for 56 it is 56.8 minus 2 into 2.7. So this is how you will get the inner dia, final inner dia 51.4 mm after this steepness. And then similarly you can calculate the 155 mm side also. So, and then your draft allowance will be like the taperness, directly you can add it like. I hope this clears.
yes, yes.
Okay. So any other student who's having any doubt in this, like, or you need some, like, we can take like 1 minute, like to digest. Like again, imagine like, so firstly you see like the problem can be complicated by a lot of things. Like I gave taper on this side this much, and then on another side this much. So you can think like how a problem, like how we like make a problem uh, to complicate it. Only one thing you did mistake, like in, and it will be like taken as negative, or like you will get negative or 0 marks. So while calculating, like we need to think from each aspect and perspective, like how complicated a problem can be made. Like if I give like if I can change the degree to radian also, and after that and if I didn't do this, like I will give different angles on each side, or I will do uh, I will make a hollow, the central part hollow, but I will add something inside it, double type of hollow or something. Yeah, lot of problems can be made, and you need to like see like how you will be proceeding it, else you might get like negative marks. Okay, So other students, please like see like please try to attempt also like Sanjay is doing. Today I don't know why there is only two students. Okay then, so after this, if we see like we read in theory about the grain size analysis. So, but it was given very like surface superficially. Like it is a very important thing like grain size analysis. If you see in terms of like mineral processing, the grain size analysis it can help to like separate set a lot of impurities. And there are other applications also like to classify different types of in basically I can say like in different fields it has different application. If you consider it from a civil engineering perspective, those person do classify their sands or soils or clay in terms of coarser and finer. If you talk about the metallurgical or materials people during after mining, like after mining when so what happens, like you are like excavating some ore from some particular mine. Okay, then like the basically the firstly what happens like those excavated parts are like in like meters of size. Okay, and it comprises like suppose if you talk about aluminum industry, like aluminum ore is generally bauxite ore and it comprises around 50% of aluminum. More than like if your ore comprises 50 to 55% of aluminum, then only it is like it is told that it is a bauxite ore or it is an aluminum ore. Or like if it is comprising less like 20 25, usually it is discarded. It is not taken as the aluminum ore. So suppose if you after a box if you are mining a bauxite ore, then you will get, you will get like meters of size of like spherical balls or not spherical, different types of shapes of meters of sizes. Now in some parts, like like if I draw, like suppose this part of this is the size of your ore, or suppose this is some random one. This this completely this won't there won't be of like aluminum. So like as I'm drawing, the aluminum is on some places and on other places generally the impurities are the SiO2, Fe2O3, because these are the abundant materials. And then there will be Al2O3. From Al2O3 you need to extract aluminum, right? So and then this aluminum is also present on these sites only. So what you will do, you need to like go to the size reduction. You know, in size reduction there are several mills, several types of grinding tools available in the market. So after milling, each material will behave differently as per their property. So this is what people, metallurgists and other mineral processing people exploited. Like after crushing, like the behavior of the aluminum part will be different. I think someone is trying to join. So the behavior of each part will be like a different one. Okay, so what happens like some people what are they like by simply grain size analysis as the each part like the failure mechanism of each part uh, uh, each constituent of the ore will be different. So like some may get finer easily, some won't get finer easy that much easily. So sometimes the sieve analysis, simple sieve analysis helps to like separate the impurities or to like enrich our product. So this is how a sieve set, it is in the topmost is located. So there are different sieves or different sizes like placed on it, and usually the suppose if I like place my size is like I know my particles are like below 1 mm. I know So then suppose this one is the 1 mm size. Then after that the sieve, which generally the rule is that after the second sieve will be like root 2 times lesser than the first one. So the second sieve is like 1 mm divided by root 2. Like that much of mm or like microns sieve you will be like putting. So this is like after putting all the sieves in this manner, I will put my sample in this. Okay. So after putting like as they are putting, after putting it, I will be using a sieve shaker. So in sieve shaking, like I put it on the sieve shaker. So why we using sieve shaker? We can do it manually, but by doing manually, sometimes biasness come. Like, but not with, what it is not with the sieve shaker part. There will be no biasness. It will be moving with the same speed, with the same RPM. Sorry, with the same RPM, with the same amount. While if we are doing it manually, there won't be like that much biasness if compared to the other one. So after like sieve analysis on each pen, like suppose this is last one is suppose 25 micron or 70 micron. So after on each pen I will get some weight, right? Some soil part, maybe some on some part we I won't get, because if maybe my some particles are not that much fine, or that it will be like ending to pan. So I get like on each sieve I got some amount. Then I will weigh my like how much amount it I will get. So I can then calculate the percentage. Like this is like on 75 micron I am having 10%, 150 micron I am having this percentage, and on another I am having this percentage. Okay. So then what you do, we make a table like this. So firstly I know like this is generally ASTM standard, like how we used to do ASTM standard, like how we calculate it. Okay. So I know weight of the container. Weight of the container means of each sieve, empty sieve, which is not having more sample. Okay. Then weight of the container plus dry soil. Like on each soil, I my some sample plus that empty part. Okay. And then weight of the dry sample I know. So I can like I will be like this table shows like sieve numbers 4, 10, 20 different numbers, like and then diameter of, so and then the diameter of the holes, like first one is like 4.75 mm, very bigger size, very coarser particles will pass through it, or majorly all the particles will pass through it. And after 4.75 my second sieve is 2 mm, the third sieve is 0.84, and then in the same sequence. So I will add like my numbers, like my values after experimentation, what I got, like my empty sieve I know my weight of the empty sieve, then mass of the sieve plus soil retained. Then I can calculate percentage on each percentage retained. Okay. Then percentage of passing. Then I will draw this curve in the Excel or any other any other tools, which will be the plot of percentage fine versus the grain size. Okay. So now after doing this, there are some terminology for there are three things like gravel, sand, fines. For that, like I will calculate D10, D30, D60. Like what are these D10, D30, D60 or D50? So like these are the generally the size, like 10 micron or 10, 50 micron. So I will take here from like and then extrapolate my line from here, and then I will plot it here, like, and I'll see like at that particular grain size what is the percentage of fines are there, what is this and that. So some people sometimes the numerical may come like this much on each sieve you got, can you give us the D50, what is the D50 size? Then people like say what is the D50. So it is just for your understanding, like D50, what D50 may is and how to calculate it. You will just randomly uh, draw a curve, and then you will see extrapolate your line from the y-axis in parallel to the y-axis, and you will see what is the D50, D30 and D60 and whatever. Not necessarily they will ask for D10, D30, D60. It may be D80 or some other diameter. So hopefully it clears a little bit more than what was covered in the class, like how the procedure happens in the lab scale and how it is a very important tool. Like people think like it is only like doing like chalni type of thing, like people say CV to hai, but it is not. It is easy, but it is like if you understand the concept, like the application of this thing, you will appreciate. You might be able to appreciate it more. Like it has like lot of applications. So can anyone tell me like, is it like they find it any useful or like it is just not?
Actually, while preparing the mold for the preparing sand molds and all, this is a very useful technique because uh, refinement of sand to put around the pattern so that the smoothness of the casting is achieved properly.
Yeah,
So for all the process of casting, this shaker experiment is very
yeah,
important.
that's true. Like as I told, like if you talk about clay, like there are different types of clay, like kaolinite, bentonite, and then depending upon the structure and all, like some are like rod like structure and some are like, we can say like if you see different types of structures, but uh, if you do grain size analysis of them also, like civil engineers do this, like, and all the metallurgists and all the mechanical engineers also need to do it some part of time to like to for their studies, right? And all of a sudden like any question may come from like any of your other competitive exams or like in the final exam. If you see like what is the gain size analysis or what is D50, D30, D60 or D10, like many people are not like aware. This is very simple thing. And this is how you plot this curve in your like Excel and all. Okay, then you like see. So now coming to the some basic things like what Professor Zaha covered in this lecture. Like these were the moisture content, clay content, permeability numbers. Okay, so there are also three things like in if you talk about the moisture content. Like if I give you a question like the weight of a certain mold or material is like 100 gram, and after it was like heating for like 105 degrees centigrade. So previously the weight was 100 gram. And after like 100 and uh, heating it at for 105 degrees, the weight got reduced to 98 gram. Or we can say like for fun, like we can say like it got reduced to like 60 gram. Okay, what will be the moisture content in this? Can anyone like tell me? Like from 100 gram, it got reduced to like 60 gram.
So 40 grams is the moisture content, right?
Yeah, 40%. Yeah, 40% is the moisture content. Moisture content is generally expressed in the percentage term.
Yeah.
Yeah, right. So there are other things also. Like if you see, some people also geotech engineers also discusses about, sorry, environmental engineers also discuss about the volatile content and other things. So that is also like it is generally said that around 500 degree, generally 400, 500, all the moisture content, all the volatile content like gets removed. So there are like different sets of experiment people do, like what is the volatile content, what will be the moisture content. So this is also a simple thing, but sometimes like all of a sudden when you see like how to calculate the moisture content, I never read it, and people forget the basics. Like at 100 degree, all the water vapor will be like completely evaporated. So this is how the moisture content. So in lab scale also, when we some environmental engineer, what they do, like they go to the landfill, like and then they collect their samples from there. The first thing after the sample collection is remove the moisture content. Like we need to calculate the weight loss. So they put it in the oven at 100 or 105 degrees centigrade for overnight, like 24 hours. This is general practice, and after then they do the weight calculation and all. And this is how they calculate the moisture content. Similarly, the volatile content is also calculated in the muffle furnace, like they put it like at around 400 degrees centigrade or 500 degrees centigrade, and then after like 4 hours or 1 hour, they calculate the volatile content also. Now coming to the clay content. So if we talk about clays, like, so these are generally the aluminosilicates or uh, so generally they are composed of silica, alumina or magnesia or both, and there are some water molecules, like basically these are seat-like structure. Clays are generally seat-like structure. If you talk about the bentonite clay, these are the seat-like structure. You see the morphology in your any of the SEM technique, you will see that these are the seat-like structure. While if you see about the some other clays are also rod-like structure and all. So if I will talking about the bentonite clay only. So in the bentonite clay, yes, these are the seat-like structure, and there are some bonds from the parallel and from between these two parallel plates. Okay, so by clay content is generally like of significance because in our like mold, because it influences the strength, permeability, and other molding properties. So if you can anyone tell me like if your clay content will increase, what will be happening to the permeability?
Permeability will decrease, is what I feel.
Yeah, that's true. Yeah, right. Yeah. So why it is happening? Because the pore size of the clay is very less. Okay, so in the and their water absorption capacity is also very high. So it if you talk about the landfills, then what current research is going on, like what happens in the landfill, people are dumping each and everything, whether it is electronic waste, whether it is solid waste, uh, in the landfill. So what happens with time, like suppose some rain came and suppose some other things came, there are some tests like TCLP, like which is like termed as toxicity characteristics, leaching potential, TTLC, and wet test. These three tests are like different for different country specific. Like US generally follows TCLP, wet and TTLC are generally followed in the European part. So what happens in these tests, like they tell about, suppose I dump something in the landfill, like will it affect my groundwater? Like if you talk about the electronic waste, suppose I take a general example of LCD screens. So in LCD screen there is like mercury content in it, which is highly hazardous thing. Okay, and if you talk about some other example uh, mm, like if you talk about fly ash, okay, fly ash is the waste of the thermal power plant industry, or red mud, which is a waste of the bauxite or aluminum industry waste. People throw them like or make a pond near the industry, and then when some rain came, what happens? It come the all the elements percolate into the our sand towards the groundwater, and our groundwater gets contaminated, which is like highly harmful. There are some examples, like this much. So there are some history known example like this much water, like I'm not remembering now, but like this water at this location got contaminated due to this and this. So what people do, like in the landfills, so there is a term called liner. So people design a liner, like anything which percolates into any material which are getting percolated. Firstly, it will come in contact with the liner, okay, and then only after your liner like has some age like 20 years, 10 years, 25 years. But in India, we don't have like these engineered landfill. We have the landfill like uh, normal one landfill, which is not which don't have any liner. So I'm talking that about that. I'm giving the example of this because uh, as the clay content increases, so what people are doing now, they how liner is made. They mix their sand or some other part with some percentage of clay, like 10%, 15%, 20%. Firstly, in lab scale, your clay content is optimized, like your strength, permeability, and crack propagation. These three things should be like optimized. That your firstly it shouldn't crack, because what happens? What's the problem with the clay? If you like I will give you example of the multani mitti. Like then some of the people might see people using this multani mitti and they put it on their face. As it loses the water, as it after some time, as it loses water, like some cracks come on it, right? Because as they lose water, like they again go to like their original shape, and again so therefore some cracks come. And that's why similarly in the case of liner, if suddenly your water gets like removed, then that shouldn't be happening. The cracks come, and strength should also be, as the clay content will increase, your strength will also increase. Okay, so that's why clay content is very important, and it can be calculated as the ratio of the difference between the uh, I think this won't be like in your topic. Okay, so clay content is generally calculated by the civil engineers. So they calculate the liquid limit, plastic limit of your soil, and then with the help of this, they calculate it. This won't be in your test, but I'm just giving you like why it is important, why its significance. And generally, clays are like have a size of less than 20 micron, but it is not the case like all the 20 micron below particles will be at the clay. It won't be the reverse one. Clay generally the rule of thumb says like it will have particle size less than 20 micron. And another thing is like the water holding capacity like is very high than the normal sands and soils. Okay, and also when there is one hydrometer test for determining the clay content, like it is a like barrel, or we can say it is a measuring cylinder of 1000 ml. Then you put some sample in it. Okay, so then slowly the clay content will settle, right? And generally the settling rate is 1 inch per minute. Below that it is a clay content. So generally, so if you could try to see, like it will be have three properties. Firstly, the water holding capacity, the size, and then the settling rate. These three determines whether it is clay or soil or simply the sand. Okay, so I spent too much time on the clay. Then finally, let's move to the permeability number. So permeability is also a very important thing. How much holes there are, how much, what will be the how your clay or sand, finally the pattern allows the gases to remove it from the cavity. And then there comes a permeability number. So I've written some numerical here, calculate the permeability number of sand if it takes 1 minute 25 seconds to pass 2000 centimeter cube of air at a pressure of 5 gram per centimeter cube through the standard sample. So can anyone tell me like what will be the permeability number? Is anyone here? Sanjay, are you here?
Yes, yes, I'm here.
Okay, okay. So generally the permeability is like calculated by the formula like or we can say like it is the rate of flow of air under standard pressure. It is like generally the formula is given by Vh by PAT, like where V is the volume, then H is the height divided by pressure, A is the area, and then T is the time. So like by generally the formula final formula become permeability is 501.28 divided your pressure and time, and then you need to like see carefully that the time unit is in minute itself, because as it is empirical formula. Else if you will be using the else you will have to use again the pH by VAT, and then the conditions are from ASTM standard. You need to take pressure, atmospheric pressure, and then other things. If you will get if you will like calculate it from the 501.28 divided by 5 into time, you need to consider calculate you need to convert it into minute itself. Time will be 1.41 something minute, then you can easily calculate your permeability number. Okay, so this
What is 501.28 here?
501 is a empirical formula. So generally the permeability is calculated with the formula of permeability number is calculated as Vh by PAT, and then the volume is fixed. Like for actually what happens, uh, the volume, the pressure, and all these things are fixed by the ASTM standard. Okay, and then so we made for the simplicity the empirical formula by putting all the things which are fixed previously. If you can also remember recall this formula like Vh by PAT, and then remembering what are the ASTM things like pressure, you need to take the atmospheric pressure, then again you will have to do that. Will be the easy thing to, because to recall all these things is very tough. Generally for the easy calculation I did it by the empirical formula from the estimation handbook. So it is like 501.28 is the empirical formula you get divided by your pressure and then time. So you will get okay.
Yes, yes, got it.
Okay.
Okay.
Okay. So now we will wrap up with these formulas, and then these MCQs will be. Then we will wrap up this session. So firstly, the first question is like a setter test is carried out to find. Can you try?
I think it is B. Is it B?
So no. So the setter test is generally in the what happens in the setter test. You completely break it, right? So break it like if you are breaking something like then the material should absorb something. Na? If you see the stress strain curve, generally the how much energy it is like taking or absorbing before breaking completely failure, and also it is the area under the stress strain curve which is called the toughness. So the setter test is generally carried out to like to find the toughness of the molding sand to know its ability to deform rather than fracture under shock loading. Okay, these are generally small MCQs. The more you will read and more you will go through the videos again, and you make notes. Okay, this is a setter test. Okay, then you will try to inculcate these MCQs with those videos, then you will get more clarity of your concepts. So generally a setter test is carried out to find the toughness of molding sand, and it is known its ability to deform rather than fracture under shock loading. Someone is trying to join. And then if you talk about the second question, the permeability of sand will be maximum for.
Coarse size and round shaped grains.
Yeah,
C.
right. And then the third question is which of the following are among the desired properties of the molding sand? Who is he? Can you please wait?
ఏమో బట్టలు ఉతుకుతానంట వద్దమ్మా.
It's 1 and 3. A.
1 second, just 1 second. Okay, yeah. So the third one is, yeah, you're correct. It is the A. 1 and 3. So desired properties are the higher refractoriness and then the higher cohesiveness. Yeah, you're right. Next, if we move to the fourth one, the ability to retain molding properties or molding sand on standing or storage refers to. It is easy.
Green strength.
Yeah, right, right. Then if we move to the fifth one, the following table shows the type of allowances and their properties, like sake allowance, distortion allowance, machining allowance, draft allowances. So you can try to like match it. So the sake allowance will be like to the original pattern dimension have to be reduced. Okay. Then if you talk about the machining allowance, okay, then it will be the depending upon the casting technique and material to cast allowances are
It's
provided for
option.
finish.
Okay, okay, okay.
Okay, what? Okay. So it will be the D. Okay. So you can like cross check and then again come to me if you found any. Do you want to say something?
Can you just switch to the previous slide for a minute?
Yeah, yeah.
Okay. So actually, draft allowance is nothing but the tapper provided for the pattern for its removal, right?
Yeah, right, right. So okay, so D is not the correct answer.
Yes, yes. Either
Yeah,
it
yeah,
is option A or B.
yeah. It is B. It is
Yeah.
not D. Okay, right, yeah, you are correct. Yeah. So now if we proceed to the sixth question, which of the following statement is or are correct regarding green strength of the mold when pattern is withdrawn to form the casting cavity? So the options are: it helps mold to retain its shape when pattern is withdrawn. Yeah, it is true. It helps mold to resist distortion or collapse when pattern is withdrawn. Yeah. And the third is like it helps mold resist the metallostatic pressure of the molten metal. No, it is not the case.
So 1 and 2
Yeah, right.
only. Option C.
Yeah, correct. Now the seventh question is like MCQ is for mass production of casting. Which among the following is most suited?
Metallic pattern.
Yeah, correct. The eighth one is like while making the mold cavity to avoid distortion, the heavier section of the pattern should be placed in. It is actually
Drag.
covered. Yeah, right. It is covered in the theory itself by the Professor Jha. And then the last two question of the today's session, like the main purpose of the seasoning of the wood is to control.
Moisture content.
Yeah, correct. And the final one is the type of pattern used for casting with structurally weak portion that are likely to break by the force of ramming is. It is the follow board pattern. So
So
these, yeah,
so
you want to
these are the assignment questions for the which you discussed right now. Is it assignment questions?
some of them are assignment, some of them are not from the assignment.
Okay, okay, okay.
Okay. So have you attempted the assignment problems?
No, not yet. I'm starting. I'm planning to start it now, so that's why I asked.
Okay. Okay. I think this week's time is it still not over the time week's time?
Yeah, yeah. Okay, so actually, Rohit, last week you mentioned that we would get the material via mail or something like
Yeah,
that.
right. Actually, I have saved it on what is happening on the YouTube is like what are the NPTEL. We are told the guidelines are that we have uploaded these on the YouTube, the video, and the material folder we have also uploaded. We have also given them, so you can like go and check the video from that. I will be uploading today's slide also, and this video is also being recorded, and that also will be uploaded on the YouTube. So any other specific thing which you need, you can tell me like beside this.
Are there any solved numericals which are available? Like, can you
Okay.
send
Yeah,
send
yeah,
it via mail or something like that?
yeah. Okay, so generally I'm trying to cover the maximum of the numericals, like to clear the concepts, like or which may come in your competitive exams or all. But I will be sharing. Okay, so I will be sharing some questions, more questions on the my folder which is shared, and then you can also uh, go to that video and that folder. So you
Okay,
can mail me then if you have any doubt, and also I will be if I don't upload it here, I you may recall this in this week. I will mail you and then upload and share that folder link with you also.
okay,
So
okay.
you have my mail ID, na?
Yes, yes, I am.
Okay, okay. So you are liking the course, the content and all.
Yeah, actually, I'm liking the course, but it is more of theory when Professor Jha comes. So,
Yeah, that's true.
it's,
So what happens when you will be giving some any exam or like this? So that theory will be will be useful for you. Uh, so what we can do, like we can do more numericals on this session. We can increase the number of numericals, but people are not joining. I don't know why. So we can in the next week. I will be what we can do. Next week is the pattern making, no? Or some other topic. Week 3 is
a core making, pattern making, and
okay.
all these things.
So there are a lot of numericals in the week 3, like mold making, core design, and all. There are also a lot of numericals in that. So I will be covering those like to the maximum of the concepts, so that your maximum of the concepts clear, and then also if some previous week's questions I may add. So majorly our tutorials will be focused on numerical solving ability of your to enhance your numerical solving ability, and theory you are already getting from the Professor Jha's lectures. Okay.
Yeah, okay, okay.
Okay, then any other questions or queries, Sanjay?
So you told that regarding the YouTube or something in the beginning. I didn't get you. What was that?
Yeah. So actually, whatever tutorial we are having, it is being recorded and it is being uploaded on the YouTube. Okay,
Okay,
so that other students who are not joining they can watch. But it takes much time, and I don't know when it will be published by the NPTEL team. So it is better if you attend the live session, and interactive section will be a better one always.
okay, okay, okay.
Yeah. So and you can mail me regarding that. I will be sharing. Okay.
Yeah, yeah, I mail you. Okay, sure. That's all.
Okay.
Nothing
Okay.
else. Thank you.
Okay, Sanjay. Have a good day. Have a good evening. Okay. See you in the next week.
Yeah, sure, Rohit. Thank you.
Okay.